Primary and secondary alcohols can be converted into sulfonate esters. And so a sulfonate ester has the general structure that is shown up here. And so the significance of doing this is that we convert the alcohol, which is a really poor leaving group. Good leaving groups are either weakly basic or neutral, and if this were to leave, that would be hydroxide, so a strong base. So it converts this poor leaving group into a really good leaving group. And so the reason why this is such a good leaving group, I'm going to draw the structure of the conjugate base so we can take a look at it, is we've got a lot of resonance stabilization. So I'm not going to draw all of the resonance structures, but we can just imagine that the charge on this oxygen, we can actually push it onto either one of these other two oxygens. So we've got a lot of resonance stabilization there. And so that is what makes that such a good leaving group, right? As opposed to the hydroxide where you'd have a localized negative charge. Okay, and so if we wanted to do further substitution or elimination chemistry with an alcohol, we'd want to convert it into a good leaving group first. And so we've seen some methods to convert alcohols into alkyl halides. And this is just another good leaving group. And so I am going to focus on a secondary alcohol to draw this because we want to take a look at what happens if your alcohol happens to be chiral. So I'm going to draw a small chiral alcohol. And we want to focus on what happens to that chiral carbon. And so the way that we do this reaction is we introduce the sulfonate ester through this chloride. And so I'm going to draw a common R group that you will see, and that's a toluene group. So this would be the structure. Right, so there's the chloride leaving group. And so if attached to that sulfur you have a toluene. Right, so toluene is benzene with a methyl group. So this is para-toluene sulfonyl chloride, also known as tosyl chloride. So you'll see it abbreviated as TSCl in your textbook and other sources. So what happens in this reaction is your alcohol is a nucleophile, and this sulfur is an electrophile. So the alcohol attacks the sulfur, and those electrons are kicked up onto the oxygen. And so what that gives us is a bond between that oxygen and the sulfur, and the oxygen is still bound to hydrogen. And so our sulfur here, we've got a single bond to oxygen where we push those electrons up. And so that oxygen has a negative charge. You have a chlorine on there, you have the toluene group, and another double bond to oxygen. And so what happens next is these electrons on the oxygen come back down to form a double bond. That's how we get the double bond in the product. And it kicks off the chloride as a leaving group. And so then we have this general structure. So our oxygen is still protonated, and now we have the bond to this sulfonate ester. So there it is. Okay, so we've got our toluene on there, and there's a positive charge on this oxygen, and that's where pyridine comes into play. So pyridine is a non-nucleophilic base. So we use this when we want a base that's going to take a hydrogen, but we don't want it to compete and do any sort of attack on that electrophilic center. And so the pyridine will take that proton. And so all we've done is we've converted our poor leaving group into a good leaving group. And so this is ready now to undergo further reactions. And so we often see this abbreviated. We don't always draw out the whole structure. So if you see it drawn like this, just OTS, these are equivalent structures. And so here's a key thing to note about the stereochemistry. That chiral carbon was not attacked at any step in this mechanism. All of the chemistry took place between the oxygen and the sulfur. So that means when you take an alcohol and you convert it into a sulfonate ester, if you have chirality, you see retention of stereochemistry. And so that is an important thing to note. Some of the other methods we have seen either racemization of a chiral center, or we have seen inversion. And in this case, we see retention.